Hi students, it's me and I'm back with 5.2 part 2, which in this case we're just going to be doing more simplifying, practicing those same objectives as part 1, which are I can simplify to show the left-hand side is the same as the right-hand side, and I understand the rules around how to prove that something is equivalent to each side. Let's go ahead and take a look at the first slide that I have for you. So the first slide today is just reviewing those same things we finished up with yesterday. So that involves, remember that step 1 is always begin with the more complicated expression. The second one is if you are unsure of where to go, try changing everything into sine and cosine. And the third is combine fractions by getting a common denominator first. Notice on this screen, I've included our identities we will use during this process. It's very important that with these identities, you recognize the different traits or trends of them. You'll see a lot of times we use the Pythagorean identities, and a lot of times we're using the reciprocal identities. That doesn't mean we don't use the others. It's just those are the most common ones we will use. If you don't have these written down, I encourage you to pause the video and write them down so you have something to reference as we move through the learning. All right. For our first example today, we are going to be looking at the proof of this. So we want to prove that the left-hand side is equal to the right-hand side. Right off the bat, I like to say, okay, it is so very clear to me that this is indeed the more complicated side of this problem. I will refer to this as the left-hand side throughout this problem. And notice that as I do my proof, I do not rewrite the right-hand side every time because it just becomes a lot of extra writing and kind of a distraction and a temptation to want to work on that side as well. So as I look at the left-hand side, again, left-hand side is here, right-hand side is here. I notice that we have two fractions, and we probably don't want to have two fractions. We probably need it to be one fraction if we wanted to simplify to something that is a single term. So to rewrite this, I would need to get a common denominator. In getting a common denominator, the easiest way to do this is to multiply the left-hand fraction, or the first fraction in this case, by the denominator of the second fraction. And by multiplying the top and bottom, it's a legal move because that purple fraction I just wrote is equal to 1. On the right-hand side, we have secant of x minus 1 over secant of x minus 1. Notice this is the denominator from the first fraction. Now, I'm going to just write my reasoning, get a common denominator. And to help simplify stuff out, I'm going to also multiply out those denominators. So we have secant of x minus 1 times secant of x plus 1. This is just going to be like kind of my work slash area to reason through and process the problem. In foiling this out, we get first secant squared of x. Outside is a positive secant of x. Inside is a negative secant of x. And the last two terms multiply to equal a minus 1. Notice that the middle terms add to 0. So I'm left with secant squared of x minus 1. Awesome. This reminds me of one of our identities. This reminds me of our cotangent identity. So we just want to kind of keep that in the back of our head as we move through this process. So I'm going to rewrite this. On the top of the first fraction, I have secant of x plus 1, all divided by what we expanded that out over there, secant squared of x minus 1, minus secant of x minus 1 over secant squared of x minus 1. All right, so we have our common denominator. Let's go ahead and simplify on the top a little bit. I noticed that we have this minus sign, and that means that's going to need to be brought into both of these terms. I also noticed because we have a common denominator, we can write it all over that. So we have secant squared of x minus 1. And on the top, we would have secant of x plus 1 minus secant of x plus 1. All right, and seeing this, I see that there is some simplifying. So in red, just to go back for just a second, red, we rewrote this as a single fraction. And then if you're looking at what I'm doing here in blue now, I am simplifying the numerator. And when I did all that, I got 2. Well, I see that we wanted a 2 at the end of our process. And on the bottom, I still have secant squared of x minus 1. Well, secant squared of x minus 1, that is a Pythagorean identity. Let's just write that out. So I believe the Pythagorean identity that we have here is tangent squared of x plus 1 equals secant squared of x. Now, we want secant squared of x minus 1, so let's move that positive 1 to the other side by subtracting it. And now we can see that, secant squared of x minus 1 is equal to tangent squared of x. Well, that's fantastic. So now we have 2 over tangent squared of x. Now, you might say, Ms. Vernon, I do not see how that equals 2 cotangent squared of x. Well, we're very close. We just have one more step. Remember that tangent and cotangent are reciprocal identities. So what I mean by that is 1 over tangent squared of x is equal to cotangent squared of x, which means this is really 2 cotangent squared of x equals 2 cotangent squared of x. We've done it. And as you learned, I like to end my proof with a nice happy smiley face because we survived another proof. It's very, very exciting when you can start figuring these out on your own. All right, let's try another one. In example 4, we are proving that the left-hand side is equal to the right-hand side. Again, I always begin my proofs by asking which side appears to be more complicated. Is it the left-hand side, LHS, or is it the right-hand side? And as you think through this, take a minute. I would vote that it is the left-hand side. Left-hand side is more complicated. Anytime you have addition or subtraction, it's typically going to be more challenging to complete. All right, so we're going to work the left-hand side. And as I look at that left-hand side, the first thing I notice is that numerator. Anytime I see a squared, I always go to my Pythagorean identities. And so when I look at that, I see cosine squared. So I think about, sine squared plus cosine squared equals 1. And I go, can I make this become cosine squared minus 1? Sure, I could subtract the 1 over. But if I subtract the 1 over, I also need to get rid of that sine squared. So I'm going to subtract that sine squared of x to the other side as well. So I did a little bit of balancing. You can definitely write out more, but I minused the 1 and then I minused the sine squared. Now this matches exactly with the numerator and I can replace it. So I have negative sine squared of x over cosine of x. Well, I'm starting to see, I know sine divided by cosine is tangent, but it's sine squared that we have written here. So I'm going to rewrite this as sine x times sine x, just to help us visualize it a little bit better. Some people might call it decomposing a squared. I'm going to break it back up into 2 parts. because once we break it back into sine x times sine x, it now becomes a lot easier to see some connections. So this part right here is negative tangent of x, and sine x is right next to it, which is what we were trying to show. So in breaking that up, it just helped me visualize it a little bit better. So, hey, guys, that was an easy couple-step proof. Nice work. Give yourself a pat on the back if you were able to see that one on your own. All right, I have one more example for us today. In example 5, we are going to prove that the left-hand side is equal to the right-hand side. So again, I always begin by determining which side is more complicated. Is it the left-hand side or is it the right-hand side? Okay, I'm going to give you a second to think about that. And I'm guessing most of you probably identified that it was the left-hand side is more complicated. Why is it more complicated? Well, it has parentheses. Now you might say, well, Ms. Vernon, you said adding is always more complicated. Well, this has adding and it has multiplication. So therefore, that's what's making it more complicated. So let's move into the process. Step 1 of this process, I'm guessing many of you want to distribute cosine of x, and I would agree with that analogy. So in distributing, remember we distribute over addition. So that means that I'm going to multiply the cosine times the tangent. This is the first term. And then this product is actually the second term. So we end up getting cosine of x times tangent of x plus cosine of x times sine of x times cotangent of x. All right, well, that sort of helped. I think we need to rewrite. Let's rewrite everything in terms of sine and cosine. This is going to help me get everything into similar terms. And that's going to help me see better if what I can and can't combine. So the first one, I have cosine of x over 1. Remember, I like to write those as fractions just because it's easier to process. And tangent is sine x over cosine x. Again, I'm going to do the same thing with the second part of this. So we have cosine of x over 1. We have sine of x over 1. And cotangent is cosine over sine. Awesome. Well, I see some really great things happening here. In the first part, I see that those divide out. So I'm left with just sine x. And notice that's what we wanted on the right-hand side. So that's looking really promising. And on the second part of this, I see the sine x end up dividing out, leaving me with cosine squared of x. Hey, that was the second part. It's done. We did it. That wasn't so bad. So if you follow that process of what looks more complicated. Now, could you have started with the other side? Maybe, but most of us would not have seen or been able to get all of that connected. So really, if you try one side and it's not working, stop. Go try the other side. You can work either one of the sides, and it's just going to help you get more agile as you work through these proofs and more capable of seeing those different ways of processing. Stick with it. I know proofs are hard, but I know you can do it.